This tutorial will demonstrate the Create Channel Bathymetry TIN with Cross-Section Template tool found in the MMC Bathymetry Toolbox and under the Channel Bathymetry toolset. The Python script was designed and developed by Gannett Fleming for the MMC Production Team. This tool is step 2 of 3 of the Channel Bathymetry Surface Development workflow if you are designing the channel from a cross-section template. At this point, step 1 is finalized. Channel cross-sections were created from the Create Channel Cross-Sections tool, reviewed, and altered if necessary. This tool will develop a channel bathymetry tin from one of 7 options. The tool uses a 2D or 3D stream centerline depending on which cross-section template is chosen. 2D channel cross-sections, a channel polygon layer, and a bare or DEM. If the user wants to apply the same template across an entire reach, then the template type can be defined through this dialog. If it is important to break the reach up into multiple templates, split the stream centerline and attribute the fields template type and template value. I will go through all the templates in a bit. Input a stream centerline layer. The layer must be 3D if creating channel bathymetry using the trapezoid, 5-point, V-shape, flow area with invert elevation, or multiple reaches template type. Drag in the channel cross-sections created and finalized in step 1, and also the channel bank polygon layer used in that same step. Choose a template type that will be applied to the entire streamline layer extent within the channel bank polygon. As a guide, click on the link to the cross-section template type diagram. The trapezoid will create a trapezoidal channel shape using the invert elevation pulled from a 3D stream centerline. A template value is required, and for this template type, this value will specify the channel bottom width as a percentage of the top width at each cross-section. Values should range between 0 and 0.95. The 5-point template type will create a channel shape using 5 points across the stream channel, using the invert elevation pulled from the 3D stream centerline. A template value is required, and for this template type, this value will specify the channel bottom width as a percentage of the top width at each channel cross-section. Values should be between 0 and 0.95. The bottom width slope is set to 3% from the center of the channel. The V-shaped template type will create a V channel shape. The template value is not included, as it will connect the average channel bank elevations to the invert elevation from the 3D stream centerline. The average flow depth template type will create a trapezoidal shaped channel. The stream invert elevations are computed by subtracting the user-defined depth, specified as the template value in feet, from the average channel bank elevation. Flow area without invert elevation creates a trapezoidal channel shape with an invert elevation computed similar to the average flow depth template. Channel bottom width is fixed at 40% of the top width at each channel cross-section. Flow area with invert elevation creates a trapezoidal channel shape with varying bottom widths based on a user-defined flow area. Minimum flow is V-shaped and maximum is rectangular. Stream invert elevation is determined from a 3D stream centerline. Flow area is computed between the average channel bank elevation and the stream invert elevation. Warnings are provided if the user-defined flow area is outside the range of flow areas at a given cross-section. Compute normal depth creates a trapezoidal channel shape with varying bottom widths based on a user-defined discharge and end value. Flow depths are computed at each cross-section using Manning's equation and a known trapezoidal channel top width. These depths are subtracted from the averaged minimum channel elevation to establish the stream invert elevation. If only one template should be applied to the entire reach, input a single stream centerline layer, which is digitized in the direction of flow. As mentioned, it can be 2D or 3D depending on what template type will be chosen. So I specified the template, and I will choose trapezoid in this case, since I have a 3D stream centerline with known invert elevations. So I'm using the tool just to determine the shape of the channel and not the invert elevation. Enter a template value. Since I specified a trapezoid as a template type, this value will define the percent bottom width of the top width. 60% is an approximate value to use for the stream I'm studying. Also define the input surface, the output folder, and also the output tin name. During the execution of this tool, a stream profile graph is plotted. It'll pop up automatically and open up a new window. It plots the left and right channel bank elevations from the input DEM. Those are the red and pink lines. Also plots the average minimum channel bank elevation along the stream, shown in yellow, the stream invert extracted from the input 3D stream centerline layer, which is in blue, and the computed stream invert given the template approach. But since I input a 3D stream centerline, the computed stream invert will not change. Close the graph to finish the tin creation. So it's applying the trapezoid template type that I chose, along with the 60% bottom width as percent of top width for all cross sections. The tin will automatically be added to the ArcMap document once it's finished completing. So my tin is finished, and after reviewing the results, I do like what I see as far as the trapezoid shape goes for this type of channel. But I think it could be more accurately representative of the channel, so I decide to split the reaches up. We'll turn off this channel tin, turn my stream back on. I wanted to find a downstream reach with a template type of 5-point cross sections and an upstream reach as a V-shape. I'll start editing the 3D stream centerline and split the reach. I'll split it at this confluence, this incoming tributary. To define a template separately for multiple reaches, the tool will work off specific fields and attributes. So these fields were automatically added when I ran the Create Channel Cross-Section tool in Step 1. I'll attribute the downstream reach as a 5-point cross-section. And define the percent of top width for the bottom width. We'll go with 50%. Now I'll attribute the upstream reach as a V-shape. I do not need a template value for this type, so this one remains null. Save my edits and stop editing, and I'll run the tool again. I'll drag the same layers in as input parameters. But this time I'm going to choose multiple stream reaches. So the attributes I input in the layer will drive the shape, and the stream invert elevations will come from the 3D geometry of the streamline features. Change my channel tin name. I'll run the tool. So this time, instead of reading the template type from the dialog, it's reading the template type from the attribute values that I input under the template type field and the template value field. The same plot will come up with similar information. Continue running the tool, close the plot. adding all the 3D layers to the tin. And then we'll add it to the ArcMap document once it's finished. So after the tool is done running, I'll review the tin. I can see the channel shape changes at the same point where I split the stream center line to specify different template types. Just to show you the difference of what they look like, I'll plot a few lines across them. This is what a cross-section plot looks like in the area that I defined the 5-point cross-section template type, so in my downstream reach. And this is what the cross-section looks at the upstream reach, where I specified a V-shape. I can decide which tin I want to use or even develop another one with a different shape. Once I have a final channel bathymetry tin, step 2 is completed in the workflow, and I can move on to the final step to merge bathymetry tins and DEM.